Hello, everyone. Today we're going to talk about molarity. Before you start watching this recording, know that you do have a workbook assignment that's going to have questions, which I will be answering throughout the recording. So while you're watching, it might be helpful to have I believe it's workbook 8.1 open as you go through. That way, when I go through and say the answers for your questions, you can go in and answer them as we go, rather than watching the video now and then going back and answering later. Whatever's easier for you is fine, but I would suggest going through the assignment as I go through this lesson. So today we're talking about something called molarity. And in order to get to that point, first we need to know a little bit about solutions and a little bit about concentration. And you'll notice that my slides have moles all over them because we are going to need to use moles in order to calculate something called molarity. So before we get there, we've got to start with solutions. So what is a solution? A solution is a homogeneous mixture. We talked about mixtures all the way back at the beginning of this year, and we said a mixture is just a combination of two different substances or two or more substances. And a solution is homogeneous if it is evenly distributed throughout and we can't see the individual parts of the solution. So an example, if I mix Kool-Aid, I can't see the Kool-Aid powder anymore once it's mixed together. That's a homogeneous mixture. This is in contrast with a heterogeneous mixture. For example, a chocolate chip cookie. I can see the chocolate chips and I can see the cookie mixture. So that would be heterogeneous, not a solution. Solutions can consist of solids, liquids, or gases, but often when we're talking about these, we're thinking about a solid dissolved into a liquid or two liquids mixed together. Either way, that would give us a liquid solution. But it doesn't have to be liquid. Solutions can also be solids or gases. Any solution with water as its base is going to be called an aqueous solution. When we're thinking about solutions, we have two vocab terms we need to think about. So a solution is a homogeneous mixture of at least two substances, and we're going to name those two substances together. We can think of it as one thing being dissolved into another thing. The substance that does the dissolving, this is going to be the substance that we have more of. This is called the solvent. In an aqueous solution, the solvent is water. The substance that we're dissolving into our solvent, so the thing that is being dissolved, the thing that there is less of, this is called my solute. Thinking back to that Kool-Aid analogy I made, if I'm dissolving Kool-Aid into water, my Kool-Aid is my solute and my water is my solvent. And then my delicious Kool-Aid beverage, that's my solution all together, all mixed together. Here are a couple more examples of solutions. So if I dissolve salt in water, this is another aqueous solution. In this case, salt is my solute. It's being dissolved. And water is my solvent. It's the thing doing the dissolving. Another aqueous solution, food coloring in water. This is a liquid into a liquid. In this case, food coloring would be the solute. I have much less food coloring than water. And my water would be my solvent. Now, I said they don't always have to be liquids, so here's a gaseous and a solid example. So if I think about the air that I'm breathing, most of that air is actually nitrogen. There's more nitrogen in the air that I breathe than oxygen. Oxygen is dissolved into that nitrogen. And I know it's weird to say dissolved when we're talking about gases, but dissolved just means that it's getting all mixed together as a homogeneous solution. So my air is a solution. It's a solution where nitrogen is the solvent because that's what most of the air is. And oxygen is a solute because it's a smaller component of that homogeneous mixture. An example of a solid solution would be steel. So if you have like a stainless steel refrigerator, that's a solution. It's a solution where that has a typo. Sorry, that should say carbon. Steel is a solution consisting of mostly iron, but it has dissolved carbon. Let me fix that. So the carbon is dissolved into the iron. The main component, the thing I have most of, is the iron. That means the iron is the solvent. The thing I have less of, the thing that is being dissolved, is carbon. So carbon is my solute. So those are all really just mostly important vocabulary terms that we'll need to know in order to talk about concentration, and ultimately we'll use this to talk about our acids and bases. So now that we have that vocabulary down, we're going to talk about the concentration of a solution. The concentration is a measure of what fraction of the solution the solute makes up. A solution with a high concentration has a higher fraction of solute. It means it makes up a bigger portion of the solution than a low concentration. Again, going back to my Kool-Aid analogy, if I put more Kool-Aid mixture into my water, I'm going to get a darker, sweeter drink, and that's going to be a solution with a higher concentration. There's more Kool-Aid per water in there. It has a higher concentration of Kool-Aid. Whereas if I put only a little bit, a small scoop of my Kool-Aid, that's going to have a low concentration, meaning there's not as much of a fraction of my beverage is the actual Kool-Aid powder. So this image kind of gives us that idea, that concentration idea in terms of our Kool-Aid analogy. So here we can see we didn't add very much on the left. That's what we would call a diluted, meaning not very concentrated solution, has a low concentration. And then on the right, we can see a very concentrated solution. That is so sweet, it would make me sick. I would not want to drink that. It is a very, very concentrated. I'm assuming this is a Kool-Aid beverage, but it's probably not actually. It might be food coloring, who knows? But it's much more concentrated on the right. And then if we think about the actual particle breakdown, I've got those pictures as well. So I can see the picture on the left. I have the same amount of solvent in all of my beverages. But as I move from the left, the least concentrated, to the most concentrated, I have a higher and higher fraction of that solution consists of those individual solute particles. So I have more solute per beverage in my more concentrated solution. There are two ways that we can think of to increase my concentration. The first is a little bit more obvious. If I increase the amount of the solute, I'm going to have a higher concentration. That one's a little bit intuitive. I'm adding more Kool-Aid, so I'm going to have a more concentrated beverage. But the other thing we can do is we can decrease the amount of solvent. So this, if I think about my Kool-Aid analogy, means if I remove water from my Kool-Aid solution, then I'm still going to have the same amount of solute, but it's going to make up a bigger fraction of my total beverage. Whereas if I go the other direction, if I add water, if I increase my solvent, then again, I've got the same amount of solute particles, the same amount of Kool-Aid mixture, but it's going to be less concentrated because now it'll be a smaller fraction of my total. And so let's look just for a moment. Okay, so this is our drink mix. So like I said, if we increase the amount, my concentration increases. And we can see an actual measurement of my concentration on the right, and we can observe that in the color of my drink mix. So again, let's say we start with water. As I add more solute, it's getting more concentrated. On the other hand, if I add more solvent, say I'm adding water, it's going to get less concentrated. If I remove solvent, if I take away the water, I have the same amount of Kool-Aid particles in there, but now they're making up a bigger fraction of my total. We'll look at some more examples here. Oh, apologies. We'll look at some more examples in a couple slides. So again, this is just recapping. So wait, how does adding solvent increase the concentration? Or sorry, decrease? And this is, so wait, sorry, say it again. How does adding solvent decrease the concentration? Why is that the case? So again, looking at it in this particle sense, as I add more solvent, in this case, the red dots are my solvent, you can see I've got the same amount of solute particles in both my concentrated and dilute solution, but when I add more solvent, my solute makes up a smaller fraction of the total. Okay, and I keep saying fraction, and the reason I'm thinking of this as fraction rather than, let's say, percentage is because we're going to use a very specific calculation to quantify my concentration. So rather than just thinking about this abstractly as more and less concentrated, we can put a number to it. We can say this one is 10 molar and this one is 1 molar. We can actually have a specific amount. We can say how much more concentrated it is than the other. And we do this using something called molarity. Molarity is a measurement of concentration. When we talk about molarity, we give it the unit capital M, and we pronounce that unit as molar. So I would say this is a 1 molar solution, or a 2 molar solution, or a 10 molar solution. And the higher the molarity is, the higher the concentration is. So again, all I'm doing at this point is I'm saying, let's give it a number. So I have a measurement now. I can say specifically, this is 1 molar over on the left. 1 molar is a pretty low concentration. Compared with on the right, this might be, for example, 10 molar, a much higher concentration. So how do we actually calculate this molarity? Molarity is equal to the moles of solute divided by the liters of solution, not the liters of solvent, the liters of the solution. So it's literally what fraction of my whole solution is moles of solute. All right, so let's think about this in terms of just conceptually before we actually start throwing numbers into it. So let's just say, for example, my solution on the left here is a 1 molar solution. I don't know anything about the mass here. I don't know what kind of solute I have, but we're just going to pretend that these 8 dots that I have on my solution on the left, we're going to say these 8 dots represent 1 mole of solute. So if those 8 dots represent exactly 1 mole, and I have exactly 1 liter of solution, then that means my fraction is the concentration on my left solution is 1 mole of solute per 1 liter of solution. That calculation tells me this is a 1 molar solution. It doesn't have to stay exactly 1 liter though. So even if I have per 1 liter, if I have a little more of this solution, if I have, let's say, 2 liters of this solution, then now I've got the same concentration. I've got twice as many moles in twice as much solution. So these two examples would have the same concentration. On the left, I've got 8 dots in 1 liter. I've got 1 mole in 1 liter. On the right, I've got 16 dots. So I've got 2 moles in 2 liters. So this is just in here to show you that no matter how many liters we're thinking about, it's the same thing. We're thinking about how many moles are there in 1 liter of this solution. If I was to pour out exactly 1 liter, how many moles would there be in that? And then we said before, increasing the solute increases the concentration. So here's just an example of that with molarity. And again, we're just going to pretend that 8 dots is 1 mole. So here, if I keep the amount of solution the same, so these examples both have 1 liter of solution, but on the right, I've got twice as many moles. I've got twice as many of those red solute dots. So that means I increased the solute concentration, or I increased the amount of solute, so I increased the concentration overall. I added twice as many moles, so I have twice as high a concentration. Or we can do the actual math and we can say, okay, if I've got 2 moles in 1 liter of solution, 2 divided by 1, now I've got a 2 molar solution. And then we also said increasing the solvent decreases the concentration. So same thing here. If I don't change the amount of solute, but I double the amount of solvent, well, now my concentration is cut in half. My concentration was 1 mole per 1 liter of solution. And now I have the same amount of moles of solute, which is still 1 mole, but now I've got twice as much solution. So I have 1 mole per 2 liters in this situation, which simplifies to 0.5 moles per 1 liter. Now, if that all felt a little abstract to you, don't worry. We're going to get this a little more concrete and we're going to do some actual example problems. But I really just wanted to give you these couple of examples to give you a bit more of a conceptual feeling about what molarity is before we dive into the calculations. So really, I just want you to keep in the back of your head when we're talking about molarity, we're saying what fraction of my total solution is my solute? How much of my total solution is just solute per 1 liter? All right, now we'll do some practice calculations. I'm going to switch over how I'm recording this so that I can go through these practice calculations. All right, let's go through these. So the first one says, find the concentration for each of the following solutions. So first thing I'm going to do is I'm going to make sure I have my formula handy. So we said our formula is molarity equals the moles of solute divided by liters of solution. So number 1, 3 moles NaCl, this is my solute, in 1 liter of solution. We're assuming this is an aqueous solution for this one. So this is going to be molarity, capital M, so this is capital M, equals moles of solute, so that's going to be my 3.0 moles, over liters of solution. So this is going to be 1.0 liters of solution. Or we can think about this intuitively. We can say, okay, molarity is how many moles of solute are in 1 liter of solution. This is 1 liter of solution, so my answer is going to be 3. So we can just think it out, or we can do the math this way. So when I do 3 divided by 1, I'm obviously going to get 3, and this has 2 sig figs, so we're going to say, oh wait, actually, this only had 1 sig fig. We didn't have this 0.0. So this is going to be 3 molar. Moles per liter is my molar unit. All right, next one. Again, we can kind of think it out if we want rather than doing the actual math. It says 7.2 moles of solute, NaCl, in my 2.0 liter solution. So I can think that out and I can say, all right, if I have a 2 liter solution, let's say this is 1 liter, this is 1 liter, the whole thing has 7.2 moles in it. So then I can ask myself, well, how many moles do I have in 1 liter? And I'm just going to cut this number in half and get 3.6 moles here, 3.6 moles here. If that doesn't make sense to you, if that's a little bit confusing, we can also just do the math. We can say our molarity equals moles of solute divided by liters of solution. So moles of solute is going to be 7.2 moles NaCl. I was a little lazy here. Out of 2 liters of solution. Remember, this is my whole solution, including the NaCl, not just the solvent. 7.2 divided by 2 gives me 3.6, and moles per liter gives me molar. And then the last one on the left says 4.1 grams NaCl in a 5.4 solution. So this specifically is moles of solute over, well, I can put my 5.4 liters of solution down, but then, I have to figure out, how do I figure out moles solute? I need that in order to get my answer. Well, I don't have moles of solute, but I do have grams of solute, and molar mass is coming back again. It's never going away. So I'm going to turn 4.1 grams into moles using my molar mass as a conversion factor. So I know my molar mass is 1 mole NaCl equals, then I'm going to go to my periodic table. I'm going to add 22.99 is the mass of sodium plus 35.45 is the mass of chlorine. 35.45, I add those together to get 58.44 grams per mole is the molar mass of NaCl. 58.44 grams per 1 mole. So that is going to be equal to, we're going to do 4.1 divided by that. And we're going to get 0.07. And we're going to keep some extra digits here. 0.071. Sorry, 0.0157. That should be enough digits for us. So right here, we had to do an extra step. We had to say, wait a second, if I'm given grams, I need to convert my grams to moles using the molar mass of my solute, which in this case was NaCl. And that gave me this number here, which I can now fill back into my formula and fill in moles of solute divided by liters of solution. So now I'm going to put in my 0.070157. Remember, we kept those extra digits just so we wouldn't lose any information here. So this is moles of solute divided by liters of solution. So I'm going to take this 0.07. Sorry, I know you can't see my calculator. 0.0157 divided by my liters of solution is 5.4. And I get 0.01299. 0.01299. I've got 1, 2, and 1, 2, so I can use 2 sig figs for this answer. So we are going to round this to 0.013 molar. So again, this seemed more complicated, but it was only more complicated because we were doing this magic that we've already done lots of times this semester. All right, let's look at these next two. So these next two ask me how many moles of NaCl are needed to make 3 liters of a 2 molar solution in water. This is something that if you decide you want to be a scientist, you will be doing all the time because you're trying to figure out, well, I need to make this solution so that I can do my reaction, and I need this much of it, and I need this much of my reactant. So this is what my concentration is. So you're going to do this kind of calculation all the time if you ever work in a lab. So what we need to do is keep our same equation here, but it's asking me how many moles of solute do I need? So I'm going to take this equation and I'm going to solve it for moles of solute. This is what I want to isolate, get by itself. So just like in algebra, right now this is being divided by liters of solution. So to get rid of that, let's do it in green. So to get rid of liters of solution, what I need to do is multiply. by liters of solution. I can't do it on just one side or I change the values. So if I do it on one side, I'm going to do it on the other side here as well. We can also actually think of this as a conversion factor because we've got liters of solution and liters of solution. And we're just multiplying by a conversion factor to eliminate our unit. But if that makes it a little more confusing, don't think of it that way. All right, so when I solve this for what I want by itself, which is my moles of solute, now my equation is going to look like this. Liters of solution times molarity equals my moles solute. So this is the same equation, just solved for the unknown that I want to solve it for. Oops. So now it's a plug and chug. I can plug in for number 4 here, my 3 liters, that's the amount of solution I want. So that's going to go here, times the molarity I want is 2 molar. And this is going to be equal to my moles of solute. So I'm just doing 3 times 2, and I'm going to get 6 moles. And this only gets 1 sig fig because I only had 1 sig fig on my 2 here. So again, I just rearranged my equation to be isolated to the variable it's asking me for, and then I plugged everything in. And now, last but not least, how many grams of NaCl are needed to make 2 liters of a 1 molar solution? So this is still the version of this equation that I'm going to use, but that's going to give me my answer in moles. And then I'm going to have to use the same process we did here to convert that back to grams. So for my last question here, I'm going to keep this same version of the equation where I'm using liters of solution times my molarity gives me my moles of solute. And I'm going to plug in everything I know, but then my answer, because liters times molarity is equal to moles per liter. So this is giving me my answer in moles. My question is asking me for my answer in grams. So we're going to solve it in moles, and then we're going to go back and turn it into grams just like we did in question number 3. Okay, so liters of solution. I've got 2 liters I'm trying to make. And I want a 1 molar solution. So this is going to give me the moles of solute. So 2.0 times 1 gives me 2.0. And I didn't include a decimal, so this is 1 sig fig. Now, if it just said how much NaCl, I could be done. But it didn't. It said how many grams. So I'm going to take this and I'm going to turn it back into grams like we did below. So we're going to use this molar mass that we calculated, 58.44 grams per mole. And we're going to say, all right, this is my conversion factor. So I'm going to take this 2 moles NaCl. And we're going to multiply by our molar mass. 58.44. And finally, we'll get our last answer here, 58.44 times 2 gives me 116.88. I think this actually does say 1.0 on the question. So we're going to say that it does because I remember having 2 sig figs when I worked this before. So this is my answer in grams. Rounding to 2 sig figs will give me 120 grams of NaCl. And again, the reason this is so helpful is because if you're in a lab, you can't measure moles. So this form of this question is exactly what scientists are doing in the lab constantly. They're saying, oh my gosh, how much of my solute do I have to add to make this given solution? And in this case, we got 120 grams. All right, remember we'll have office hours twice this week. Keep an eye out on the homepage for when those office hours are. And if this is confusing or you want to see some more examples together, I'm happy to work with you on these during those office hour sessions. All right, thanks everyone. Bye-bye.